शुरू करते हैं।
Hello and namaste to all of you. I am Ajay Rotela, welcomes you all in the third talk of GeoVigyan International Webinar Series on Earth Science, and I am your host for the day. Before we start today's talk, let me explain some rules for the webinar. If you have any queries during the lecture, please write that query in the YouTube live chat box. We will take your questions during the question answer session. We will send the attendance and feedback form link in YouTube live chat box during the lecture with a 45-minute time limit. So going towards today's talk, the topic of today's talk is Fluid Inclusion Studies, Concept and Application of Geology. And today we have with us Professor Pankaj K. Srivastava. Professor Srivastava is working as a professor of economic geology in a University of Jammu. After completing Ph.D. in applied geology from Indian School of Mines, now Indian Institute of Technology, Dhanbad, he served different organizations like Awardee, Institute of Himalayan Geology, Dehradun, and University of Rajasthan, Jaipur, in different capacities before finally joining University of Jammu as assistant professor in 1996. He has done his postdoc from Technical University, Germany, and worked there as visiting scientist. He is a DAAD fellow and is Young Scientist Project Awardee of DST, Government of India. Professor Srivastava has more than 28 years of teaching and research experience in the field of ore geology, mineral exploration, mining geology, fluid inclusion, and geochemistry. Professor Srivastava has taught various subjects at UG, PG level and has guided 18 PhD and MPhil students till date. His main area of research involves genesis of hydrothermal mineral deposits with the help of fluid inclusion and geochemical techniques. Tungsten, rare metal, and gemstones deposits associated with acidic magmatism are of special interest to him. Apart from this, the gold deposits of Mahakhosal belt, fluoride deposits of Rajasthan and Ladakh, Saibhiri deposits of Padar, Jammu and Kashmir, and carbonate-hosted lead and zinc and magnesite deposits of Himalaya have also been studied, particularly with reference to evolve of ore-bearing fluid and their genesis. 6 research projects sponsored by various agencies of Government of India have been completed till date. He has authored more than 50 research papers published in different reputed scientific international and national journals and 5 edited book volumes. He has published more than 100 papers in different international and national seminars. He has also organized various national seminars, workshops, summer schools, Inspire camps for school students, and North Zone Youth Festival. He was also selected section recorder, Earth Science System section of Indian Science Congress for 2 consecutive years, 2014-15 and 2015-16. Professor Srivastava has a vast administrative experience and has served University of Jammu as the University Syndicate member, Dean Student Welfare, and Chairperson Campus Security and Head of Department of Geology. He is also a member of Syndicate of University of Kashmir. At present, he is heading the Jammu and Kashmir State Eligibility Test Agency and is coordinator of Entrance Exam Cell of University of Jammu. He is also an external member of Board of Studies, Central University of Sikkim Gangtok and Cluster University of Jammu. We thank Professor Srivastava sir for accepting our invitation to the webinar talk. Now I will call Professor Srivastava sir for his valuable words. Over to you, sir.
Thank you, Ajay, for a very big introduction. And at the outset, I thank GeoVigyan for giving me opportunity to interact with the young students of different part of the country as well as other parts of the world. Today, I will be talking about the fluid inclusion study, its concept and applications in geology. Particularly, this talk is organized to popularize this technique, that is the fluid inclusion, and This technique is one of the very important technique for understanding the paleofluids and understanding the various earth processes. It is widely used in the ore geology and petrology, but it can also be used in other part of the earth sciences, like your structural geology and other things. So we will be talking about that. And the scope of this particular talk is to popularize, as I told you, is to popularize the technique among the young student and researcher to understand various earth processes. And it is organized in different things, and you will, at the end of the talk, you will be able to understand what are the fluid inclusions and how they are entrapped, how they are classified, what kind of data can be generated from the fluid inclusion studies, and what can be interpreted from the fluid inclusion studies, what kind of information can be collected from the fluid inclusion studies. And in the last, I will take some case studies to understand how it is applied in the various aspects of the geology. So that's how I organized my talk, and I think that I have tried to put it in simple words, because many of the young students of UG are also here. So there is a wide range of I am told that there is a wide range of the audience in this gathering. There are UG students, PG students, research scholars, and some faculty and other working professional geologists as well. So for them, for some of them who are in this field, that may be a kind of basic, but for the students, this will be a good knowledge to add in their knowledge base. As such, this topic is not covered in the, it's covered in very small portion in some of the syllabi of the economic geology or the petrology. But as such, it is a very vast topic, and let us try to understand how it works. So friends, let me start with the basic thing, that is, because we are talking about the fluid inclusion, it means we are talking about a particular thing, that is fluids. And fluids, as you know, they are a very important part of the earth evolution and various formation of the various minerals, metals, and other things, rocks, as well as fluids are also important for the civilization, because we are also dependent upon water, and therefore whatever we are seeing as fluid, particularly the natural occurring fluid, is broadly termed in one thing, that is the natural geofluid. So geofluids can be defined as any subsurface fluid which is natural occurring, like you may call groundwater as a geofluid, you may call basinal brines as a geofluid, you may call geothermal fluids as a geofluid, ore fluids, hydrothermal fluids, magmatic fluid, whatever is naturally occurring and is subsurface is normally known as the geofluids. So, and you also know that fluids are very important because many of the minerals, they have their origin from the they crystallize from the some fluid material or some material which is fluid in nature. Now we are calling fluid because we are not taking the state of the matter. Fluid may be liquid, may be in liquid state, it may be in vapor state, it may be in or gaseous state, or it may be a mixture of the liquid, solid, and gas. So whatever is having some kind of fluidity is defined as the fluid. So if we see the whole issue of the geofluids, so we can divide the fluids into geofluids into two major groups. One is the modern free fluid, which is present in hydrosphere, atmosphere, and is also used in or getting got through the exploratory drilling in the cellular lithosphere, or the gases which are emanating from the Earth's interior and volcanoes. They all are the free fluids, and they are termed as the modern free fluids, geofluids, one group. And the second group is the paleofluids, which participated in rock and mineral forming processes in the past. So geofluids which have been participated in the various rock and mineral forming processes, which may include rock forming minerals or the ore forming minerals, ore minerals, whatever. So if those kind of fluids are termed as the paleofluids, and these paleofluids are basically, we are interested in the paleofluids because what information we are getting in terms of the today's or what is present with us is the rock which has been formed, or the rock consisting of the minerals, or ores which are consisting of the ore minerals and gangue minerals, and they ultimately crystallized from fluid, which may be hydrothermal fluid or the ore fluid or the magmatic fluid or whatever, or even the brine, basinal brines. So from solid to know about the conditions in which these fluids are formed, we can use various techniques. So to characterize this paleofluids, we can, if we are able to understand or characterize these paleofluids, we can very well explain how the minerals are formed, or how the mineral was formed, or from which fluid, and what was the geochemical characteristics of that fluid that can be calculated, or whether it was the magmatic fluid or hydrothermal fluid or any other basinal brines. So you can, if you understand this paleofluid characteristics, you can very well tell about all these things. And also you can tell about the conditions, the physicochemical conditions under which the minerals are formed. So we as a geologist are more interested, though there is another branch that is to study the modern fluids, but because we are studying mainly the rocks and minerals, so in that case we are more interested in the paleofluids. So how to study this? Now there may be only two methods. One is that you use the indirect methods by reconstructing the fluid properties from fluid mineral equilibria using the thermodynamics and phase rules, etc. And the another method is direct method, if we can sample the paleofluids. Now this for many students, young students, this may be a kind of surprise how to calculate, how to sample the paleofluids, and that is there where we are having the whole gambit of the fluid inclusion studies, and therefore the direct method of studying the samples of paleofluid is the main method which is implied in the fluid inclusion study. So, question by many can be whether we can sample the paleofluid or not. So, my answer will be yes. We can sample the paleofluids. How? That we will understand now. But before we understand that, let us see some of the thin sections. Now, if you see this thin section, you will find that there are certain lines. I have shown them with arrows. And if you see them, these arrows, you can visualize that there are certain kind of lines or certain kind of trails of the some inclusions are there. So various trails of the inclusions. We normally see it in thin sections, but we ignore it. As a petrologist, we normally ignore it. It may be the air bubble, or it may be a problem due to the thin section making or something like that. We call it and move away. But for fluid inclusion petrologist, this is one of the very, very important thing, and he keep on multiplying it, magnifying it, and try to see what these are, whether they are the air bubble due to the formed due to the malfunctioning of the thin section making, or they are real fluid inclusions. So if you see in this thin section, you will find number of such trails are available, and there are certain dots which are bigger in size also. So just like inclusions are present, and some big inclusions are also present in this slide. So let us take another example. This is again altered albitite from Rajasthan, where you can see this section, and you can find that again there are number of trails of the inclusions are present. So these trails are having certain kind of continuity, and some of the trails are cutting across the mineral boundaries. So let us understand what these are. And these are the fluid inclusions. These are the areas of our interest as a fluid inclusion geologist or fluid inclusion petrologist. We normally take these things very seriously, and then these are the basically the fluids which are entrapped due to when the mineral was forming, was crystallizing from that particular fluid. So they are the mother liquor as such. They are the mother liquor which are present, which are the sample of which are present in the present day after even the million of years. So what are fluid inclusions? So you have seen that these are the fluid inclusions. So what are fluid inclusions? Friends, fluid inclusions are basically a boon for the geologist, and this is something which has come from the imperfection. Imperfection, when I say imperfection in crystal growth. Now that is a defect, crystal defect, but that is a boon for the geologist or petrologist. How it is? Now you can see this figure, which is atomic force microscopy image, which is showing a pit. This pit is 80 nanometer pit, and 500 into 300 into 80 nanometer. This is the size of this pit, and this is in albite. When albite was going, this pit was formed, and this pit is basically a crystal defect, and that defect may be because of number of regions that we will study afterwards. Now, when such pits are formed, then the fluid from which this crystal is going is these pits are filled with that particular fluid, and then upper layer on this pit is formed. So this pit was sealed by another layer of the crystal. So now this fluid got entrapped into this microcavity in the crystal, and because it is thermally sealed, so it remains as it is throughout its development. There are certain changes takes place after the entrapment, but it remains like that one. So because of they are the macro cavities, very very small cavities and thermally sealed, so they remain as it is. And we see such kind of defect in all kind of crystals, whether it is any crystal which has developed from the fluid will have some kind of cavities, and fluid may or may not be trapped into it. So fluid inclusions are normally developed because of the imperfection growth of the crystal or defect in the crystal, but they become boon for the geologist. This trapped liquid or trapped fluid can be anything. It may be liquid, vapor, or supercritical fluid, or it may be a silicate or sulfide or carbonate melts or anything. So fluid inclusion, when we talk is it in a very broad term. It is the inclusion, or it is the fluid which is basically maybe a silicate fluid, or it may be a hydrothermal fluid or any other brines. So it's a very broad term. So many of the earlier workers used to have two different terminologies, that is fluid inclusion and melt inclusion. Melt inclusions are those inclusions which are having the silicate melt entrapped into them, and fluid inclusions are those inclusions which have the fluid and which remain as a fluid during the ambient cooling to ambient temperature. So that's how the classification is there. But to define it, now you can again see this diagram, the lower photograph, which is from the quartz, and you can see the quartz is having a lot of inclusion trails. Some of the inclusion trails are cross-cutting each other, and some are isolated. Some are present as the cutting across the crystal boundaries also, and some are along the various crystal boundaries. So you have the all kind of fluid entrapment, and this lower picture is from the Great Mica Belt of Jharkhand, Bandarchua area. So you may have the different kind of means you can have the fluid inclusions in all kind of minerals, right? So how to define the fluid inclusion? So the modern definition of the fluid inclusion comes from the Bodnar in 2017, and he defined it as the small, usually microscopic droplets of the fluid that are trapped in the crystal during their initial growth or post-growth during healing of fractures in the mineral. So both kind of fluid, whether they are trapped during the growth of the mineral or trapped after the growth of the mineral during the fracturing or deformation, so that can be taken as the fluid inclusion, and that is the modern definition of the Bodnar. So in this definition, you cover both the things. You cover the silicate fluid also, or melt fluid also, as well as you also cover the normal hydrothermal fluids or the carbonate fluids. So all kind of fluids are covered in this definition. So now we can say the fluid inclusion refer to any inclusion that trapped a phase that was a fluid at the temperature and pressure of the formation, regardless of the phase state of the inclusions as observed at the laboratory condition. Whether you are observing it now as a fluid or as a solid state, as a glass, if it was in the fluid state at the entrapment of the at the time of entrapment, then we call it as a fluid. So it's nothing to do with the phase which are present at the laboratory condition, means after million of years. So we call it as a fluid inclusion. So it may include some of the solid inclusions also. Now let us understand, is it a new phenomena or it's a very old geological phenomena, known phenomena? So fluid inclusion are known long back. It's not a very new thing which are known in 19th or 20th century, but they are known long back. And the first scientific writing about the presence of the fluid inclusion was by Abu Raham Ali al-Biruni. He was a Uzbek scholar of 11th century, and he called fluid inclusion. He saw the fluid inclusion in the some of the gemstones and called them as the juice of the earth. So he was the first one to describe fluid inclusion in the gemstone, and he saw it through lenses that there are certain inclusions, and he called it as a juice of the earth. So, and then various workers started working on the inclusions in 1672. Boyle has given the moving bubble concept, that he has seen inclusion where the bubble was moving in the liquid. So he described it as the moving bubble concept. And then Davy was the first person. Davy and Brewster were the first person who did the chemical analysis of the fluid inclusions, and they also described the solid phases and the immiscible liquid phases in the fluid inclusions. But the major thrust in the fluid inclusion research was by the work of the Sorby. Sorby, S.C. Sorby was the main person who did a lot of work on the inclusions, and he even not only sketched the fluid inclusion, but also sketched the melt inclusion in the rock. And these are the hand sketches you can see on the side of this slide, that they are the hand sketches of glassy and gaseous inclusions in feldspar phenocryst in the trachytes, and then they were drawn by the Henry C. Sorby in 1858. So fluid inclusion research got real growth by the work of Sorby, and he has written a number of papers on this thing. And then in recent years, the two places, the equal growth has taken place in 20th centuries. Russian schools have done a lot of work on the fluid and melt inclusions, and the European schools have done also equally good work in the 1950, 1970. They have done very good work in the fluid inclusion. So there were two schools, European schools and the Russian schools on the fluid inclusion research, and a lot of development in the fluid inclusion studies has been done by both these schools. Since Russian school was writing mostly in Russian language, so their work was not much recognized in the West world, but they were their work was equally important and very well taken afterwards, and when they were translated in English. And the Yermako was the pioneer worker of the fluid inclusion in the Russian school, while Roeder was the pioneer worker in the European school. And you will get number of papers of the Roeder and Yermako. Now, where we can see the fluid inclusions, we can see the fluid inclusions in some of the main minerals. Though the inclusions can be present in all the minerals, but because you need to see them in microscope, under microscope, so there we have tried to classify the top 10 minerals where fluid inclusions are most commonly studied and reported. So they are the quartz, fluorite, halite, calcite, apatite, dolomite, sphalerite, barite, topaz, and casterite. These are the main minerals where most of the studies are concentrated because of their transparency and because of most of them are the colorless minerals. But in colored minerals also we can find fluid inclusions. In garnet, people have studied fluid inclusions in garnet. People have studied fluid inclusions in olivine. So number of in pyroxenes also people have studied fluid inclusions. So you can study fluid inclusions provided if they are very good visible in under the microscope. So most of the transparent minerals and most of the minerals which are having good transparency and they are the robust, because if you heat mineral and if the vapor pressure got increased under the fluid inclusion, it can burst and it can be leaked. So that's how the you need to understand how to study and which mineral is to be studied. It depends upon its robustness, transparency, and occurrences. So these 10 minerals are most common minerals where you can study the fluid inclusions. And the occurrence of the fluid inclusions or the distribution of fluid inclusion in single crystal, it depends upon the primary growth conditions and partly on the post-crystallization history of the samples. Roeder noted that there are inclusions in a given sample which increases with decreasing inclusion size. Means if you are having a small inclusions, then there will be more number of inclusions in a particular volume of the mineral. And in some quartz and calcite, you may have around 10 raised to power 9 fluid inclusions per cubic centimeter. So in 1 cubic centimeter volume, you may have 10 raised to power 9 number of fluid inclusions, and they may be very, very small. Right, so it depends that how small it is and which mineral is having. Quartz and calcites are the and fluorite are the minerals which contains lot of fluid inclusions, and therefore they have been studied a lot. Now, how big can inclusion be? Inclusions can be in fatmograms or nanograms. They may be very, very small, and some inclusion can be very, very big. They may be of the size of the which can be visible through naked eyes. So from dust-like particle to a very big size of 1 millimeter size, you can have the fluid, one or even bigger. So, but most of the inclusions, the bigger inclusions are very, very rare, and the most of the inclusions, they are less than 100 micrometer size. And the typical size range in which the most of the inclusions are present are the 2 to 20 micrometer. And bigger inclusions are very big. So now you can just imagine what is the size of the the dust particle, you can, in the upper diagram, you can see the dust particle is a small dust particle of 100 micron. The human hair is normally of 70 microns, and the fluid inclusion you can have 3 to 20 microns. So you can see what is the size of the inclusions which are present in the or which we study under the microscope. So they are very very small. Human hair जो होता है उससे भी कितना छोटा होता है, that you can always observe with the fluid. So and on the other side, this is the smaller inclusion, but on other side you can see inclusions in naked eyes. Those fellow students or the students who have observed some of the geo labs or the geo museums where some of the specimen gem specimens are kept, you can see, particularly I am talking about the Awardee Institute museum. If you go there, you will find quartz crystal which is containing inclusion with moving bubble, and you can see there. So in this picture, you can see that you can see some of the inclusions through naked eyes also. So though they are rare, but you may have this kind of. This amethyst crystal is 7 centimeter crystal, and in this you can see a few millimeter large fluid inclusion. So that is one inclusion which can be seen through naked eye. This is the emerald. The second picture, greenish in color, is the emerald gemstone, where you can see the fluid inclusion through naked eye, though they are the dust-like particles. And in topaz also you can see the inclusion. So you can see the inclusions both by naked eyes. They are mega inclusions, they are macro inclusions, and then they are micro inclusions. So size is ranging from few micron or less than 1 micron to more than 1 millimeter. So that is how the fluid inclusion can be observed. Now, these are the fluid inclusions which you can see in some of the minerals. You can, in the left hand side photograph, you can see the fluid inclusions in trails, and these trails are cross-cutting each other. While in case of the Joint quartz, you can see the inclusion along the growth plane of the quartz. So in various growth plane, you have the different type of inclusions. In one growth plane, you can see maximum inclusion. So that is the which is shown by arrow. In this growth plane, you can see maximum number of fluid inclusion. So depending upon the circumstances of the development or the condition under which a crystal is growing, the number of inclusions depends, and also the size of the inclusion. Okay, so how does the inclusions are entrapped? Now, as you know that any crystal grows as a unit cell. So you grow one by one, systematic block growth takes place. And if there are some imperfection in growth, then the fluid remains there, and the next block is next block can seal that particular cavity, and you may have the sealed cavity containing some kind of fluid inclusion. So that is one thing, that is the imperfection or irregularities in the crystals growing surface, and that may be because of the structural failure, that may be like dendritic growth may be there, or the fracturing may take place, or the subparallel crystal growths are there. Impurities, if there are some impurities on the growing surface, then also you may have the imperfection or you may have the etching and the partial dissolution, which can be triggered by an interrupted growth. So all these phenomena are responsible for the development of cavity and entrapment of the fluid inclusions. So each regularities, whatever we have talked here, they are they serve as the potential fluid trapping sites, whether it is the dendritic growth pattern or the fracturing or the subparallel crystal growth or the impurities on growing surface or the partial dissolution or etching. All these things can have potential site for fluid trapping. So they can form the intracrystalline inclusions, and this uh, may be like this in case of the crystal growth. They are the various conditions under which the crystals are growing. Now you are seeing that a crystal is growing in A diagram. If you see, if there is a rapid growth, then there is a feathery growth cover, and then this feathery growth is covered by the upper layer of the normal growth, and then in this the cavities are formed and the crystal is fluid is trapped. So there are subparallel growth, then also fluid can be trapped. Partial dissolution, this is the partial dissolution method where the fluid can be trapped. D is the fracture. If a fracture is developed during growth, along that fracture fluid can move and then can get trapped into when the fracture is sealed. So all these phenomena can have the kind of development of some cavity and then entrapment of fluid inclusion. Now you can see there in some of the photograph, you can see that there are certain kind of negative crystal development, negative cavity development. Means the crystal unit cell that is there, and then that comes in form of the cavity. So such kind of things are very common in the fluoride, in calcite. You may have the ROMs develop in fluoride. You may have octahedral cavities develop. So all these phenomena can be, and in case of the some quartz or topaz, you may have the prismatic phase developed. So you may have the negative crystal shaped inclusions in many of the samples, and you may have a sealed crack inclusion, sealed fracture inclusions, where you may have the some kind of melt inclusions available, or the fluid available, or even sometimes you may have the petroleum inclusion. So this diagram, that is the right hand side photograph, it is showing the petroleum inclusions in the calcite veinlets. So you have the such kind of development, and such important phenomena takes place during the growth of the crystal or also after the growth of the crystal. So and that is studied, and we try to find out. Now there may be homogeneous trapping or the heterogeneous trapping. Now you know, if there is a equilibrium condition, fluids are there, they can be trapped as a homogeneous fluid. But if there is certain kind of condition where you have the boiling condition, then in that case, what will happen? You will get two kind of fluids trapped. One may be the liquid and vapor kind of fluid, where the vapor is low concentration and liquid is high concentration. And when the boiling is taking place, then vapor will be more in the upper part, and therefore you may have a vapor-rich inclusions. So you may have the different kind of trapping. You may have the heterogeneous trapping, or you may have the homogeneous trapping. In homogeneous trapping, only one type of inclusions are trapped. In heterogeneous trapping, you may have different type of inclusions can be trapped. So this is one example of the heterogeneous trapping, where you have the gaseous inclusions. You can see G represent the gaseous inclusions or gas-rich inclusion, and AQ is the aqueous-rich inclusion. So in AQ, liquid is more than vapor, while in G, vapor is more than liquid, or gas is more than liquid. So this kind of trapping is the heterogeneous trapping, right? But if you are getting only the aqueous inclusions in one place, that is the homogeneous trapping. Another important aspect is the phenomena which normally takes place after the entrapment. After the entrapment, number of changes takes place in the fluid inclusion, and uh, you may, because fluid is trapped, so fluid may be having liquid and gas, and after cooling, the gas may be separated out from the liquid, and fluid may be divided into liquid and gas, and you may have the gas, vapor and liquid together. Or even after cooling, the if the salinity is very high, then some daughter crystals can be formed from that particular fluid. So you may have the halide crystals developed, silvite crystals developed, anandrite crystal developed, or even sometimes if it is melt inclusions, you may have some kind of silicate minerals developed. But another important aspect is the necking down, because what happens when a fluid is trapped, and when the after the entrapment, the deformation takes place, or the fluid records certain kind of changes, means because it is having the vapor inside, or having the fluid inside, so it will have the its own fluid pressure, and because of that pressure, the fluid may try to, or the cavity may try to re-equilibrate in the new condition of the pressure and temperature, and because of that, you may have breaking of the fluid inclusion. So from one fluid inclusion, you may have the three fluid inclusions at the end, and that is known as the necking down. So it's a kind of a stretching of the fluid inclusion which takes place, and ultimately you may have different type of inclusions, that is the necking down. But this kind of inclusions from the temperature of trapping to temperature of necking down with time, they are of no use, and they are not used for the genetic aspects, and therefore, because the conditions have been changed, and they have re-equilibrated themselves to new conditions, so that's why they are not used. So if you want to use a fluid inclusion for the recording correct formation temperature, in that case you need to have the inclusions without necking down effect, right, or without any re-equilibration. So here all these phenomena, and if you see, you can very easily identify, because if there is a necking down, then you will find two tapering areas in the two fluid inclusions. So the figure, the photograph, which is the in right hand side, right most hand side. So you can see in this that it's at the about to get neck down, and about to be separated into two different fluid inclusions. So that can be very well, and you have the two tapering points from which it can be separated, so that you can know that whether your fluid is neck down or not, and whether you can use it for the further studies or not. So we talked about the re-equilibration, and what exactly determine that which inclusions can be re-equilibrated. So the mineralogy, inclusion size, inclusion shape, and the fluid composition, these they determine the re-equilibrium conditions. Bigger the inclusion, more the chances of the re-equilibration. Smaller the inclusion, less chances of the re-equilibration. Prismatic the inclusions, more chances of the re-equilibration. So elongated inclusions can get easily equilibrated. So all these depends upon these four factors. Now, if you see, this is a condition in which the internal pressure versus hardness of the mineral. So what you are seeing here, the harder minerals have lower re-equilibration conditions, and the less harder mineral will be re-equilibrated very easily. So that is the graph, and you can see the internal pressure which mineral can be re-equilibrated very easily. So this is the range of the pressure for the calcite, barite, sphalerite, and fluorite, where you can see the variation of the pressure as a function of inclusion size as well as a function of the hardness of the mineral. Similarly, if we see this figure of the board knot, again we can see that the inclusion size, the bigger the inclusion size, the more chances of the re-equilibration. So that is you can see the volume of the inclusion as well as the inclusion diameter, and the bigger the inclusions, more chances of the re-equilibration. At very less pressure, it can be re-equilibrated. And experimental data is also there. You can see that with time the size is changed, and you may have the a bigger inclusion may be re-equilibrated to a smaller inclusion with time. So again, you may have the kind of temperature and pressure conditions which can suggest that there can be changes after the entrapment. So this diagram or this sequence photograph is suggesting that at the time of the entrapment, the fluid inclusion was big in size, but after say 5,621 hours, it has become re-equilibrated and become smaller in size. So size can also be re-equilibrated. So many times such things have to be seen and try to find out whether your inclusion is primary in nature or it has been re-equilibrated, because that will affect your interpretation. Shape-wise, your inclusion may be, as I told you, your inclusion may be of different shape. It may be irregular, it may be prismatic, it may be negative crystal size, it may be rounded, it may be sub-rounded, it may be elongated. So so all these things we record, because that will give us some kind of idea. Because if you are getting a negative crystal shape inclusion, that points out to be an inclusion which has been trapped during the growth, right? So the first few photographs where you are seeing the negative crystal shape of the cavity, and inclusion is trapped in negative crystal cavity. So then they are the very, very important one, and they are formed at the time of growth. Now, based upon the this thing, the next thing which we carry out is the classification of the fluid inclusion. Now, the classification can be done on number of ways. There are number of ways to classify the fluid inclusion. They are based upon the room temperature, phases present at room temperature. They are also upon the compositional basis, and they are on the genetic basis, that how the fluid inclusion is formed. Now, based upon the your room temperature, phases present at room temperature means that is around say we call room temperature at 25. Normally in fluid inclusion laboratory we maintain that temperature at 25, 24 like that, so that our phases don't change. much. And in that phase, if we see the temperature, the phases present in the inclusions, they may be monophase, means having only one phase, either the vapor or the liquid. They may be biphase, that is, they may have the liquid and vapor, or they may be polyphase, that is, they may have the liquid, vapor, as well as they may have the solids with them. So the three diagram you can see, you may have the liquid and vapor, you may have the liquid, solid and vapor, and you may have the liquid, vapor, and immiscible liquid also. So you may have the two different things. Then compositional basis. So compositional basis means what is the composition of the fluid which is present inside the fluid inclusion. So it may be aqueous, it may be carbonic, it may be aqueous carbonic. So based upon the composition of the fluid, we can classify it as the whether it is aqueous carbonic, or the melt inclusions, or it may be genetic. That is the primary, whether it is formed with the formation of the crystal, during the time of the formation of the crystal, or then it is known as the primary. And if it is formed after the formation of the crystal or the post crystallization, then that is known as the secondary. But there may be certain cases where you are not able to fix the genesis, whether they are secondary in nature or the primary in nature, then they are known as the pseudo-secondary. So there are various ways to classify, but the most famous and most important base of the classification is the genetic classification, and that genetic classification is in terms of the primary, secondary, and pseudo-secondary. Now, in this diagram of the Kirchhoff, you can see that the fluid inclusion are in different manner. You can see the inner side where the growth planes are present. Some of the inclusions are along the growth planes, so they are the primary because they are along the growth planes. There are certain inclusions which are isolated, they are also primary. So primary inclusions are formed during and as a direct result of the growth of the surrounding host crystal. That is the definition of the primary inclusions. Secondary inclusions are those inclusions, you can see here some inclusions which are cutting across the boundary of the crystals, and it means they are formed after the formation of these minerals along a fracture plane. So they are formed along a fracture plane, and they are known as the secondary fluid inclusion. So such inclusions which are formed along a fracture plane are known as the secondary inclusions because they are formed after the formation of that particular crystal. And in this, the central one, central grain, if you see, you will find one trail which is not cutting the boundary of the crystal, but it is present in form of a trail and not cutting across the boundary of that particular crystal. So such kind of inclusions are known as the pseudo-secondary inclusions. They might have formed during the formation of the crystal as a fracture, growth fracture. Okay? So when crystal was forming, it may have developed some kind of fracture which was healed afterwards, and then such minerals are, because they are not crossing the boundary of the crystal, they are considered as the pseudo-secondary, not a secondary. So they can be used for some kind of studies. So these are the three important kind of inclusions which are classified based upon certain phenomena. And how they are formed, we have talked about it a lot. Along the growth plane, if there is some fracture and it got healed, then you will have the pseudo-secondary. If it is along the growth plane, then you will have the primary, and if it is cutting across the boundary of the mineral, then that is the secondary. So that is the classification. Now I will just give you a demo of how the minerals are formed, how the fluid inclusions are formed along the growth plane. Here you can see the growth plane of the crystal, and along the growth plane some aqueous solution is moving and getting trapped. So you will have the such kind of trapment of the primary fluid. But when there is a fracture developed along the crystal, and the aqueous fluids are trapped into that, then you will have the such kind of entrapment. So within a crystal, if you have such kind of growth of the inclusions, or such kind of presence of the inclusions, you can call them as the primary inclusions or secondary inclusions, depending upon your. Now again, you may have the secondary inclusions may have the different kind of bubbles present, or different kind of liquid or bubble ratio present. Though they are the same aqueous liquid, but they may have the different liquid vapor ratio into. So that is also one of the important things. They may have the different temperature and pressure. If you calculate the temperature and pressure, they may have the different pressure and temperature than the primary. So that is the totally one thing. So the question is that why we, which kind of inclusions do we study? Whether we study the primary inclusions or we study the secondary inclusions. Now it depends upon what kind of interpretation do you want, what kind of study you are doing, right? So if you are studying the genetic aspects of the mineral, in that case you are more interested in the fluids which has formed during the formation of the crystal. It means you are interested in the primary origin. But if you are studying the deformation cycle of the any rock, in that case you may have the number of fractures develop, and you may have to study the secondary inclusions as well. So you need to understand what kind of study you want to do, and which inclusion has to be selected. Mostly we select the primary inclusions because they give you much more reliable information about during the growth of the plane. So how to identify? There are various ways to identify. You can see the growth plane. If the inclusions are along the growth plane, they are surely the primary inclusions. Or the inclusions which are occurring in three-dimensional random Fourier distribution, they are also primary inclusions. Sometimes isolated inclusions are primary inclusions. So many of these things, but how to see the growth plane? Many times you don't see the growth plane in the mineral. If there are certain minerals like zircon, you can see the growth plane, but some of the fluorite, you can see the color banding or growth zone. But in some of the minerals, you are not able to see the growth zone. So for that purpose, you need to use the cathodoluminescence or the X-ray excitation to understand, to see the growth plane of the mineral, and then try to find out whether your inclusions are along the growth planes or not. And secondary inclusions, again, they occur in the planar groups, outlined hilt fractures. They are flat and very irregular in shape. Snaking down and re-equilibrium effects are very common in the this thing. So what you are seeing in this photograph, you can see that there are two parallel, two vertical fractures developed, and along that number of inclusions are developed. So they are the secondary kind of inclusions. So now we come how to study the fluid inclusions. Now, what you have seen that they are micro in nature, therefore you need to make thin sections. But how thin it should be, whether the thin sections are sufficient to study the fluid inclusion? No, because fluid inclusion are the three-dimensional having three-dimensional cavities. Therefore, their sections should be slightly thicker than the thin sections. So what we do, we first grind and cut and grind the section like what we do for the thin section. Then we polish one side of the thing, and then we grind it and the reverse. We do the reverse mounting. That is, the side which has been polished is mounted, and then another side is grinded, and then that side is also polished. So it's a double polished wafer we use for fluid inclusion study. So it's slightly thicker than the thin section, and depends upon the which kind of mineral we are using for the study of the fluid inclusion. So fluorite may have the thicker wafer, while the fluorite and calcite may have thicker wafer, while the quartz may have thinner wafer. So it depends upon, or the even the tourmaline may have the thinner wafers. Sapphire will have the thinner wafer. So like that, you will have to different thing. And then what we do, we take out the wafer from the epoxy by washing it in acetone and other things, so that epoxy is removed, completely removed, and then we take the wafer, completely clean wafer, for further study. So we can see that these are the various kind of variation in the fluid inclusion content. And what I was talking, that classification based upon the phase at room temperature. So these are the phases at room temperature. We may have the only liquid or vapor. We may have both liquid and vapor, but their ratio may vary. Liquid may be more than vapor, liquid may be less than vapor. There may be a multi-phase inclusion, like you may have the multi-solid liquid and vapor. You may have the immiscible liquid, that is, two liquids may be present which are immiscible in nature. Carbon dioxide is one of the such thing which is immiscible in the water, and at high temperature it becomes miscible. So at low temperature it becomes immiscible. So you need to have the a particular temperature at which it looks at the immiscibility is developed. Then we can identify the daughter minerals which are developed after the entrapment, and they may be halite, sylvite, hematite, and necrolite. So all these minerals may be developed, and based upon their optical properties, we identify them, that what are these daughter minerals. Concept of the fluid inclusion assemblage has come up because what happens now, if we study the fluid inclusion, there will be number of inclusions present in a rock or in a mineral, and each inclusion will give you some kind of data, temperature and salinity data. Now, if we take inclusions which are trapped at one point of time, then they will have the same kind of phases, they will have the same kind of temperature, and they will give you same kind of salinity. They should. So, based upon that thing, criteria has been given to identify the fluid inclusion assemblages. Now in this, if you see, you have one isolated inclusion, one along the growth inclusion. So inclusion which is present as isolated inclusions, they are one type of inclusion. The inclusions which are present in growth planes, they are another type of inclusions. Another inclusion, FIA, and the inclusions which are pseudo-secondary, they represent another assemblages. So that's how we can classify them in different kind of assemblages. In this diagram, you can have six type of assemblages present into this. So isolated, growth plane, pseudo-secondary, secondary, and you have the another vapor ratio के basis पे, on basis of the immiscibility, you have the another one. So you have the different type of inclusions, 6 type of inclusions you can, assemblages you can identify in this. So once we identify and once we categorize them, different type of inclusions, as well as we identify their shape, size, all those morphology and classification, then we try to find out what kind of data we can actually obtain from the inclusions. We can obtain the temperature of formation. We can also obtain at what pressure the fluid was trapped. We can also obtain the composition of the fluid, and we can also obtain the salinity or density of the fluid which was entrapped into the cavity. So from one fluid inclusion, we can identify, or from the fluid inclusions in the mineral, we can calculate, because what we are having is the mother liquor, so we can know the composition of the fluid. We can also know the at what temperature and pressure the fluid got entrapped into the this thing, or even we can create the formation temperature, and then the density or the salinity of that particular fluid. So both physicochemical conditions of the formation of fluid or entrapment of fluid or formation of the mineral can be obtained from the study of the fluid. Now, there are methods to do that, and the technique which we use is known as the fluid inclusion microthermometry. So, fluid inclusion microthermometry is done on the microscope fitted with heating and freezing stage, and that stage can be fitted on any good petrological microscope, and but that microscope should have the long view objective. So that is one criteria for the having the microscope. So microthermometry is done on the heating freezing stage, and this is the setup. Various kind of stage you have. You have the USGS system, that is fluiding system, or the most popular system, that is the Lincoln system of the fluid inclusion. So various labs are having different kind of system. One is having the USGS system. Another one is having the Lincoln system, and both are very popular. But Lincoln has taken, because of its less space and less things present into it, we use more commonly Lincoln system. These are two type of the geological heating and freezing stages which we normally use. The one which is the THSMG 600, which can heat a sample up to 600 degrees centigrade and cool up to minus 140 degrees centigrade. And the another one where you can see the golden thing, this is only heating stage, and this is used for the melt inclusions. Here you can heat the sample up to 1500 degrees centigrade. So you can heat it to a great temperature. So it is used. So now done on SG600 and thermocouples, and thermocouples are heating silver block. These thermocouples are platinum thermocouples, and they heat the silver block on which we keep the sample, and because silver block is equally heated, so sample get also equally heated from all the sides, and then the changes in the phase is seen through microscope. So that is how we have set up the This is the construction of the heating freezing stage in this. Now, the one thing which you must take care when you select a petrological microscope for the fitting, heating, and freezing stage is the working distance of the objective. So it should have the long working distance objective, your microscope. Then only it will be useful. So we normally do three kind of experiments with the fluid inclusions, and these are known as the microthermometric analysis. They are the heating analysis or the heating experiments, cryogenic experiment or freezing experiment, and the chemical analysis or microanalysis. Now, what we do, we will take a very simple example because I'm not going to take all kind of fluid inclusions. There are various type of inclusions, but we are taking a simple example of aqueous inclusion where you have a liquid and vapor condition, like what you are seeing in this photograph. So this slide is will give you an idea how the heating and freezing is done. So what we do in heating, we calculate, because what we assume, there are certain assumptions that the fluid entrapped was homogeneous at the time of entrapment. Means it was in one fluid. It was mix of the liquid and vapor. It was not separated as the liquid and vapor, and it was trapped as a fluid. Now, after the cooling, or after a million of years, the fluid got separated in terms of the liquid and gas. So two phases are developed, and so what we, as per this assumption, when we heat it, we try to find out at what temperature it becomes one, again homogenized. So we note that temperature, and because it is a thermally sealed inclusion microcavity, so it's a very closed system. So nothing is going out, nothing is coming from outside. So what we can see that when it is homogenized, we call it as a temperature of homogenization, and that temperature of homogenization is the minimum temperature of entrapment. That is the minimum temperature of entrapment. Why it is minimum? Because we are experimenting this thing on the atmospheric pressure, but the fluid was entrapped at the another pressure inside the earth. So we need to know at what pressure it was trapped. Then we will give the pressure correction, that we will afterwards you will see. So with this few slides, you will try to understand how the heating experiment is done. You put your wafer on the stage and thermal stage, and then you start heating it. It's all computerized, and you can see that thing heating on the screen. So now, say at the room temperature, that is at 25 degrees centigrade, I start heating it, and when the heat is taking place, what you can observe? You can observe that there is a change in the bubble size, and slowly bubble is going down, its size going less and less, and at 350 degrees centigrade, there is no bubble, there is no gas. It's completely homogenized. Now, this is one where the liquid vapor homogenized into liquid, so it has converted into liquid phase. But there may be another thing also, that liquid get changed into vapor. So depending upon at what phase it was trapped, whether it was vapor phase trapped or the liquid phase trapped, that we can understand by homogenizing it. So this temperature 350 degree here is known as the temperature of homogenization, and this is the minimum temperature at which the mineral got entrapped. Right. Then we start cooling it, and as we cool it, then we get again the same volume of the vapor and liquid. So this is how we do the heating experiment, because in that the getting back the vapor is important, so that you know that nothing has gone out, the liquid or vapor has not leaked from the cavity due to heating. Sometimes some of the minerals like fluoride or some other minerals, when you heat it too much, then they get cracked and the cavity get cracked and the liquid moved away. So that is also one thing which is there. Similarly, if we have some kind of multi-phase inclusions where we have the daughter inclusions or the sulfides present into it, we try to heat it and we try to find out the temperature at which the solid got melted and a total temperature at which the total homogenization takes place. Sometimes solid get melted after the homogenization of the liquid and vapor phase, and sometimes the solid melt early. So depending upon the conditions, we can call it the total homogenization temperature more than the dissolution temperature, or total homogenization temperature less than dissolution temperature. So here we calculate three things: temperature of dissolution of solid, temperature of total homogenization, and temperature of liquid and vapor. So that we calculate. You can see in this sequence photograph that how the homogenization is taking place. In the first diagram, first photograph, you can see that the solid first dissolved and the homogenization takes place. In second B diagram, you can see that the solid and vapor both got homogenized together, and in third one, the solid got homogenized later than the vapor got homogenized. So all the three categories are there, and based upon that we calculate, and sometimes this may help you to calculate the salinity of the fluids also. So this is one experiment where you can see the change in the behavior of the solid phase and dissolution of solid. So the next one is the freezing thing, that how do we freeze the or cool the sample. So when we do cool the sample, what happens? As you know, that salinity in aqueous fluid or in any kind of fluid, if you just say, for example, if we see the kulfi kind of thing, we put salt into the ice. Why we do that? Because to reduce the melting point of the ice, and therefore we if you increase the salinity, the melting point is lowered, right? So what happens once you do the this thing, then ice will form at the negative temperature. Otherwise, if it is a pure water, then it will be it will freeze at 0 degrees centigrade ideally, right? So what we do in this, we cool it to super cool our fluid, because slowly cool karne pe, if we do the slow cooling, then what will happen? The fluid may get metastable. So to avoid that kind of condition, we super cool it. So what we do, we first super cool to minus 100 degrees centigrade or minus 90 degrees centigrade. So what happens? Your complete fluid get converted into ice, and the vapor which is present, either it will hide within the ice, or it will remain as a compressed vapor bubble. So then slowly we heat it, and after heating we see the phase changes. So what will happen? We start heating it. We start heating it, and we see the first melting temperature when the ice is start melting, and first melt start appearing. So that temperature is known as the temperature of first melting. And as you know, this temperature of first melting depends upon what kind of system it is, whether it is H2O NaCl system or H2O KCl system or H2O NaCl CaCl2 system, what kind of salt is present into the brine, that can be defined by this first melting system, first melting temperature. And then we again heat it, and slowly when we heat it, ice get removed and vapor comes to its original shape, and the no ice is present. So that is known as the temperature of last ice melting. So temperature of last ice melting depends upon the salinity of the fluid. That is, what is the salinity of the fluid? On that basis, the last melting temperature. So we can calculate the system, ecosystem, or the salts present into the system, as well as we can also calculate the salinity of the fluid which is present in the fluid. So both things can be calculated on basis of the freezing studies. So this is the real picture of the freezing studies, and you can see that how the solids get changed, and this is one experiment of the freezing experiment. So at -7, the very small amount of solid is there, and at -5, -6.6, it's completely dissolved. So temperature of ice melting is known as -6.6, and temperature of first ice melting is at -21.2. So this helps. Similarly, you may have the different kind of inclusions. This is one sketch for the immiscible inclusion, that is the CO2 aqueous carbonic inclusion. And in this, CO2 is present as immiscible fluid, and you have the CO2 liquid, CO2 vapor, and the water. So similarly, we may have the petroleum or the oil present into it, but oil sometimes is not identified by the normal light. So we use the fluorescent light to identify the methane or the oil present into the. So this is how fluorescence light is used, UV fluorescence light, and in that we can identify the presence of hydrocarbons. So how do we identify what kind of dissolved species are there and what kind of system is there? So it's based upon this eutectic temperature, that is the temperature of first ice melting, and based upon that these are some systems for which eutectic temperatures are fixed. And if your temperature is around these temperatures, eutectic temperatures, you can know what kind of system, what kind of salts are present into your. So this thing has been laboratory developed, and the phase diagrams for such systems are present, and you can calculate your value for how much salt is present into your ecosystem. So what is there in theory? This is a phase diagram of the H2O system and H2O NaCl system, H2O NaCl system. This is taken from the Sheffield. And if you see this, the T1 is the temperature where the ice starts forming, because you have the solidus and liquidus present here. And this is the at T1, the ice should start forming, and at T2, that is around -20.8, the whole system should be converted into complete solid. This is the theoretical thing, but in practice, because of the meta-stability, this temperature of -20.8 is not received, and therefore what we do, we first supercool our fluid, and then we go up to T3, and then we start heating it to get the real position. So that is T2 and then T1. So that's how we do in the system. So how do we now see the phase diagram? This is one example I am giving you. You may have the number of phase diagrams for different systems, and based upon that you can calculate the pressure and temperature. So temperature you have calculated through homogenization temperature. Now if you have the isocores developed, and you know that what is my isocore, what is the density of my fluid, then in that case, if your fluid is trapped at this point, PT and TT, that is trapping point of the temperature and pressure, then your fluid will remain homogenized there. But if you start lowering this thing, then what will happen? The fluid will follow this isocore, right? Because of its density, it will follow this isocore. And at point this one, that is where it is reaching the LV curve, the first ice will form, right? So at this point of time, your first ice will form, and then you may have the such kind of system where you have the complete vapor development. So that's how you can calculate if you know the temperature of homogenization, and you know the isocore, that what is the density of your fluid, then you can calculate the pressure. And the change in the temperature and pressure calculation, so at this point of time, because you are getting the complete ice at LV curve, so at this is the temperature of homogenization. But your fluid was trapped at PTTT condition, that is the red point, upper red point. So PTATT conditions can be obtained by knowing the isocore's value, and once you know the isocore value, then that correction of the temperature can be given, and that is known as the pressure correction. And you can calculate from minimum entrapment point to minimum entrapment temperature to the real formation temperature. So that is known as the pressure correction. So TT minus TH is known as the pressure correction. Okay. So that's how we calculate this thing. And this is again a phase diagram of NaCl H2O, which can give you some idea how to calculate the salinity. Because if you follow this temperature, if you have the temperature of last ice melting, you can plot it on this, and you can get the weight percent NaCl, that is salinity of the fluid. And once you get the salinity, you can calculate the density of the fluid also. Right, so this is how your fluid occurs along the isocore. The same thing which we have seen earlier is given in this diagram also. So, friends, again, the salinity is determined by various ways. You can determine salinity by this knowing the last ice melting, or you can calculate the salinity by knowing the halide dissolution temperature, depending upon various diagrams and what type of fluid you have. There are a number of methods by which you can calculate. There are now we do it through softwares. Various systems are available, and for different systems, modeling for the temperature and pressure is given as such. So I think this is one Hall et al. And Bodnar, all these, they have given various model for the calculation of salinity and density also. Once you know the salinity and phase relations and homogenization temperature, then you can calculate density. You can calculate density on basis of the degree of fill. You can calculate density on basis of the other diagrams also. So I am not giving you all the diagrams because because of the limitation of the time. It's a whole big subject. So I'm just giving you an idea that what you can do with this tiny fluid inclusion. And once you do that, then you can determine the pressure also through fluid inclusion by calculating these four things, four principal methods. That is the vapor pressure at time of the TH. You can also know the isochores if you have the isochores, that is the line of having equal density. If you have the isochores and independent geothermometer, then also you can calculate the density. Similarly, from dissolution, if the temperature of solution is more than the temperature of homogenization of the liquid and vapor, then also you can use it for calculation of pressure. So this is the one diagram, that is the intersecting of the isochores, and based upon that we can calculate the temperature pressure condition. Similarly, this is one example from the Bandhanwara area where we have calculated the pressure and temperature using the different type of isochores of the different type of fluids. One was the carbonic fluid, another was the aqueous fluid, and we calculated the isochores when they cut across, that is the maximum and minimum temperature pressure condition under which this was formed. So now to interpretation part of the data, the best way is to plot the temperature and salinity. Temperature and salinity, and once you do that, then in that case you can have different trend, and based upon that trend you can this is a simplified interpretation given by Shepard, that trend 1 will give you the mixing of cooler and less saline fluid. Trend 2 will give you isothermal mixing with fluid of contrasting fluid. Trend 3 will give you boiling with slight cooling, and trend 4 will give you simple cooling. Trend 5 will give you leakage of inclusion, and trend 6 is necking down of inclusion. So 5 and 6 are normally not used, right? So 1, 2, 3, 4 you can use for interpretation. And then comes the chemical analysis or the analysis of the fluid, and for that we may have the two type of methods. One is destructive method, another one is the non-destructive method, and based upon that we can calculate the chemistry of the fluid. And in solid phase we can use the scanning electron microscope or X-ray diffraction or the scanning electron microscope with the DX. And aqueous solution, we can extract the fluid and then put it into the by just drilling the fluid inclusion and then extracting the fluid and putting it in the various equipment, whether it is AS or LAICPMS or SIMS. We can calculate the what kind of liquid chemistry is there. If there are only gases, then we can use the mass spectrometry and gas chromatography for calculating, for knowing the chemistry of the gas. Non-destructive method, we can use the petrography, that is the visualized light microscopy, or the microthermometry also, because we have seen that the last ice melting temperature or the first ice melting temperature, we can know the system. We can use the infrared microscopy for opaque host minerals. Laser Raman spectroscopy is very, very commonly used nowadays, and the Fourier transform infrared microspectroscopy. All these methods can be used to know the chemical constituents of the fluid inclusion and various phases present in the fluid. This is one Raman spectra for some of the pure H2O, and we can know what kind of liquid is present, what kind of gas are present into the system. So with this, we come to the last part. That is the because I am seeing the time also, and that time is now running away. So we quickly I will go through the last part. That is the application part. And in application, you can use this fluid inclusion in petrography, petrology, that is knowing the petrogenesis, knowing the ore forming processes. You can use it in the deformation and metamorphism processes. You can use it in gemology. You can use it in petroleum exploration, and nowadays people are also using the fluid inclusion stratigraphy. So based upon your one kind of fluid inclusion which is present, you can do a lot. Mainly the petrologist and ore geologists, they have been using it, and lately the metamorphic petrologist and means petrologists are same. Now some people have started using it for the structure, a lot of people, and the recent one they have started with the petroleum exploration, because you know that in petroleum you get the fluid which was formed and get during it can be entrapped in the cement or other diagenetic minerals, and then you can know whether that system has been formed petroleum or not. So this is one example of the from Balda tungsten deposit. This is one example, and in this, if you see the temperature and density of the homogenization temperature and density of the fluid have been plotted, and you have seen that there are different type of fluids. One fluid is plotting at the higher density and higher temperature, while the other fluids are low density and low temperature. And there is a medium fluid which is having the moderate density and moderate temperature. Now, there are certain conditions where there is a mixing of the fluid. So this complete phenomena, if you plot these samples on these kind of diagram, you will be able to understand the how your fluid has evolved from this system. So the hydrothermal fluid has evolved from high temperature, that is the magmatic fluid, and then it converted after mixing with the aqueous fluid. It has formed the separation of the carbon dioxide from the magmatic fluid has taken place, and then you have after mixing it has taken out, and there is pure aqueous fluid, and then at the last when it is temperature has become low, and temperature has the density is also low, or salinity has also become low, then the mineralization is stopped. So that's how the you can know the complete history of the mineralization and ore forming processes through fluid inclusions. This is another example where you have the Balda Degana tungsten belt, that is in the Rajasthan, and you have plot this into the this thing, and by seeing this, you can say that their bimodal data is there, their bimodality is present, and you have one kind of high salinity, high temperature fluids, and another one is low salinity and moderate temperature fluids. And there is a area where there is no fluid, and that suggests that there is some kind of metastability was developed, and the mixing, after mixing the aqueous fluid with the magmatic fluid, you get the mineralization in complete belt. So that's how, and boiling is also there, because we can see that there are certain kind of inclusions which are overlapping, and they are of different type. So boiling can also be seen in this. So based upon this, we can give you a complete hydrothermal fluid evolution, and based upon that, we have given this kind of evolution history for the tungsten mineralization in the Rajasthan tungsten belt, where the fluid evolved from the magma, granitic magma. By cooling granitic magma, the magmatic aqueous fluid got evolved, and you have the high temperature, high salinity aqueous fluid, and then you have the high temperature and low salinity carbonic aqueous fluid. From magmatic aqueous fluid, they are separated out, and then they mixed with the cooler meteoric water when they got evolved, and during the mixing time, maximum deposition of the tungsten took place in the well. And as the temperature goes down, there is a seizing of the tungsten mineralization. Similarly, we have seen in the Panthal magnesite deposit of the JNK. Again, there is some kind of mixing is there, and the here the temperature is very low. So what we have suggested that this is a kind of subvertical bands you can see in the green thing, and that is because of the subbrinal fluids present into the area. Similarly, it can be used in gemology to understand the province from where the gem has come, because in gemology you know that the gemstone's genesis, from which area it is coming. For example, if sapphire is from the Burma or Myanmar, it has a more value. If the sapphire from the Kashmir, having the maximum value, or ruby from Myanmar is having good value. So genetic name is also important from where the gemstone is coming. And again, the fluid inclusions and the solid inclusions help to understand the province. Then we also, the fluid inclusions helps in understanding the whether your gemstone is natural or synthetic, whether your gemstone is heat treated, and naturally, like any other mineral, you can know the formation condition of the gemstones. So in gemology, it is quite often used to know province and the natural status of the mineral as well as its formation condition. So I told you why this recognition, provenance and recognition of heat treatment is important, because if it is like untreated Burma ruby, then it was sold for 36 lakhs $30,000. But another one, if it is treated, then it will be sold in a very low value. And the same untreated Burma ruby is very costly, you can see, than the untreated Chimavaz ruby. So again, you can see that cost depends upon the genesis of the gemstone. That is very, very important. Then in the metamorphic process, to know the pressure and temperature condition of the maximum metamorphic condition, you can use the fluid inclusions. So this is one from our research only, our research group only, how we have calculated the pressure temperature conditions. Then you can use it in knowing the deformation. As you know that deformation, all the in the various stages of deformation, number of quartz veins are developed, and in different phases of deformation, the quartz veins are developed. So you may have the generations of quartz veins within an area, deformed area, and if you sample the quartz veins or calcite veins, you may have the different kind of fluids present in it. Now this is a photograph from the paper Srivastava and 1990 paper. And in this you can see that there are different type of veins are developed. You have the strike veins, you have the cross fold veins, cutting is strike veins. So cross cutting structure is also present. So if you sample this thing, you will find different kind of fluid inclusions, and you can always know the you can plot it, and when you plot it you can find that there are different type of clusters developed. So we suggest that they are at different deformation state. So you have the cross fold veins developed at a very low temperature and having low salinity. Then the strike veins and the bedding plane veins are having the high temperature and high salinity. So depending upon the deformation condition and the temperature pressure, you can calculate the values. The same thing here also, you can say how the movement of the metamorphism takes place, or how the deformation has taken place into the area. So next is the your petroleum exploration. You can use it in petroleum exploration, as I told you that the petroleum can get entrapped into the orthogenic cements or the orthogenic growth of the minerals, or in the diagenetic overgrowth. And if you sample it and analysis it, then you will be able to understand whether this particular area was, or this particular rock was having the sand, having the petroleum at one point of time or not, and whether it has some petroleum has migrated from that particular area or not. So it is very, very important to understand the secondary migration and primary migration of the petroleum by using the and you can know the path also, how the migration has taken place. So as I told you, in case of the petroleum sections, the normal light will not function, so you'll have to fit your microscope with UV light, so that you can have the fluorescence of the petroleum, and you identify the petroleum in the inclusions. And the last application is the fluid inclusion stratigraphy, and that is the stratigraphic mapping of the paleofluid chemistry through bulk mass spectrophometric analysis. And we normally, this is the latest thing people are doing in fluid inclusion, and they normally do the fluid inclusion chemical analysis, and then from various strata, and then correlate it with the stratigraphy. So that's how things are developed in the fluid inclusion. So in conclusion, we can say that we can study mountains through microscope using fluid inclusion. So what we have seen, a tiny thing of nano size, that has given us some idea how the orogeny, or idea of the genetic processes or ore forming processes or the petrogenesis, that has given us big idea of the deformation. Anything you can, various earth processes can be identified by studying the small, tiny fluid inclusion. The not only the geological and mineralogical sciences, but you can also use the various planetary samples and see the fluid inclusion or melt inclusion, and study the petrogenesis from that. So we can say that inclusions are object of great wonder and natural beauty, and are of great importance in geological history. So with this, I think these are the few papers and books from where I have taken some of the diagrams and photographs. So I thank them for such a wonderful work. And if you want to study more, you can see these books. These are the books which are very, very important in fluid inclusion studies, and they are the basics. So whether you read the Reuter Fluid Inclusions or you read the Shepherd Practical Guide to Fluid Inclusion Studies, or the lecture notes on the fluid inclusions of analysis and interpretation, or the geofluids, all these books are available in all the important libraries, and they are very, very important. Apart from number of research publications, out of which one publication in Lithos, which is totally devoted to the fluid inclusion studies. It was published in 2003. That is also very, very important. So for more studies, you can refer to these books and other things. So with this, I think I stop my talk, and thank you very much for your patient hearing, and I hope I am able to inspire you to see the fluid inclusion from very important studying earth processes. And they are not the tiny dust particles on your thin sections. They are very, very important samples which can be studied to give you big interpretations. Thank you very much. If you have any questions, I don't see any question in the box, but if you have any, you can.
Thank you, sir, for this valuable and informative talk. We have questions in YouTube live chat box, so
Okay.
we will take from that. Now we will take some questions.
Right.
The first question is, sir, how to do fluid inclusion provide information or help in oil and gas exploration?
I think in last few slides I have told you that in oil and gas exploration, what you want to know, where the fluid has been formed, where the petroleum is formed, and how it has migrated. So normally you don't know the path, how it is migrated. So if it is migrated through some sandstone or other rocks, then in orthogenic growth of that thing or diagenetic growth of that thing, the petroleum will get entrapped, and you will have the very good sample of the petroleum from that particular and that's how you can use that path to know where the fluid has moved, and you can use it as the petroleum exploration.
Yes, sir.
So second question is, what is its practical use about magma? Right. So Surendraji, this is the when you have the any kind of melt inclusion. The melt inclusion is the part of the magmatic inclusions, magma only, and that is entrapped, and you can identify and you can model it complete petrogenetic history out of the studying the melt inclusion, and lot of good work is being done. In India, unfortunately, we are not doing a lot of work on melt inclusion, but lot of work is being done in throughout the world on the melt inclusion, and to understand the petrogenetic processes. Rongpi is asking, as a US student in geology, what are the basics that we should know 100% of it in order to understand fluid inclusion much better for future research studies. Number one, you need to understand that fluid inclusions are the tiny part of the mother liquor. So don't see that whatever bubble you are seeing in your thin sections, don't let it go like gas bubble or anything. Try to magnify it and try to see whether it contains some kind of fluid inclusions, right? Whether it is some silicate part or the fluids and vapor or the so if you magnify it, you will see that there are certain kind of fluid inclusions present into that. And if fluid inclusions are present, then sample it and then try to find out what kind of a study you want to do, whether you want to do the deformational studies, you want to know the metamorphic processes, you want to know the orogenetic processes, or you want to work for the petrogenesis. You can do it accordingly. Surendra is asking, how can we understand this in practical perspective? Practical perspective, I think what he want to ask, what I understand from his question is that how best we can use in practice. So you can use it, and if you see there is one journal, GeoFluid, and it is totally devoted to the geofluids studies. So you can see how much work is being done in the area. Any Ore Geology journal you see, you will find a lot of work is being done on the fluid inclusion. Any petrology journal you see, a lot of work is being done on the melt inclusion. So it's having the practical aspects, and you need to first understand the thermodynamics very well. If you want to really do the fluid inclusion studies, you should be good in the phase equilibria studies and thermodynamics. Then only you will understand how the fluids have moved and what kind of phases have developed and how the various phases are developed. Negative crystal shaped inclusions, kindly elaborate. Shashank, when I say negative crystal shape, now you see how the crystal developed. Crystals are developed on basis of the unit cells. And what is unit cell? This is the smallest part of the crystal. For example, if you have an octahedral crystal, so the unit cell will be of octahedral shape. Now, if the cavity is developing in that thing, and then you have a cavity which is octahedral in nature, that is known as the negative cavity, negative crystal shape, because it's not a crystal, it's a cavity. So it's not a positive thing, it's a negative thing, and that's why it is known as the negative crystal shape. And if the fluid is trapped, then that is known as the negative crystal shape fluid inclusion. I have shown you some of the fluid inclusions photograph where you have seen the octahedral fluid inclusions in fluorite or the prismatic fluid inclusion in topaz. So you have seen that in the earlier diagram. I think I am clear to you, Shashank. And then Pushpak is asking, what is the temperature of homogenization in fluid inclusion? Pushpak, when we heat the fluid inclusion, then what happens? You get, there is an assumption in fluid inclusion studies that the fluid was trapped as a homogenized fluid, right? It was either in terms of the complete liquid or was complete vapor or whatever. So it was in homogenized state. Now what we are seeing today, after cooling and all those things, after million of years, what we are seeing is two heterogeneous nature of the fluid. And that heterogeneous nature, when we heat it, because of its closed system, nothing goes out, and it got heated and it converts into one phase. That is, vapor changes to liquid or liquid changes to vapor. So you have two phase earlier, that is the liquid and vapor. Now it has converted into one phase. So that is the temperature at which it is converted into one phase is known as the homogenization temperature. And homogenization temperature is the lowest temperature of entrapment, right? So this is the minimum temperature of entrapment. If you want to know the temperature of formation of that particular fluid, then that particular mineral, then you will have to give the pressure correction, right? Okay, so next question is okay. Bibhu is asking, what is negative crystal state? I have already answered that. Then Kaji is asking, when fluid inclusion take place, it remain as same as fluid or change into crystal chemistry or others? Please tell me in detail. See, it's a very small nanometer cavity or micron cavity, in very small micron size cavity, and it is immediately hermetically sealed, means complete closed system is developed, and therefore not much changes takes place. But if it is, you have the melt inclusion, then you may develop some kind of glass or some kind of crystals, or even you can trap some silicate minerals into the cavity, so which was being crystallized at that time. So you have the entrapment fluid and post entrapment changes also. So it's not remain same, but some changes takes place depending upon what is the fluid inside. So chemistry doesn't change. You asked whether crystal chemistry changes. No, chemistry doesn't changes. Whatever fluid is, because it is a closed system, so chemistry doesn't changes. By the trapped, Saurabh is asking, by the trapped bubble, can we define the pressure of the ore formed during the ancient time? Yes, we can define the pressure. We can calculate the pressure, not from the trapped bubble, but from the complete fluid inclusion studies. So we will have to calculate the temperature of homogenization. We will have to calculate the salinity and density of the fluid, and then of all kind of fluid inclusions. And if they are trapped in simultaneously or coeval, then we will have to have the various ways to know the, if there are two type of, then we will have the cross-cutting isocode method, or if it is boiling, then we have the pressure vapor pressure method to calculate the pressure of the formation. So yes, we can calculate the pressure, and we have discussed it in presentation. Fluid inclusions are mostly common in what kind of ore deposits? Fluid inclusions, as I told you, is a product of imperfect development of the crystal. So it will be present in all the crystals which are formed from some kind of fluid, whether it is a magmatic fluid or ore fluid or hydrothermal fluid. So in all kind of ore deposits, you will get the fluids. Where the means placer deposit, you may not get the kind of fluid which will give you the formation of the placer deposit. But otherwise, where the mineral is formed from the fluid, you will have the fluid inclusion. Depend upon whether your mineral is transparent or whether your conditions are like that you can study those fluid inclusion. Because many times, if you have a dark colored mineral, the change of phase is not visible in the when you do the experiment, and therefore you face difficulty. And therefore, most of the minerals which we use in the fluid inclusion studies are the transparent minerals, like the 10 minerals I have given. Saurabh is asking, if there are deformed rock in the outcome, can we identify what are the primary fluid inclusions present in that rock? Yes, you can identify some of the primary fluids, but they will mostly get re-equilibrated. but certainly you can have the in the formed rock. What we calculate is the maximum condition of the metamorphism. So whether it is the what was the metamorphic path it has taken. So we can calculate the metamorphism, whether it is going in prograde or retrograde. So we can know this kind of thing. And yes, primary inclusions will be there, but they will get slightly change their re-equilibration as per the metamorphic conditions. The particular trace elements present in the fluid inclusions can indicate which type of ore deposits be present over an area. Normally, it is not the trace element in the fluid inclusion, because what we get entrapped in fluid inclusion is the aqueous part of the inclusions, and in that aqueous part, the trace elements are present, but they are not in a big quantity. So, mineral exploration, it is used. Fluid inclusions are used in mineral exploration, but yeah, what kind of ore deposits are present, that cannot be told by the trace element, but other methods are there to understand the what kind of deposits will be there. I can show you one diagram. I think, yes. If you see this diagram, is it being seen? Yes. If you see this diagram, there are various type of deposits. You have the Kurko type of deposits, low gold deposits, epithermal deposits, iris type of carbonate hosted ledging deposit, Mississippi Valley type of deposit, tin tungsten deposit, skarn deposit, porphyry deposit, and there are certain areas where this temperature and salinity is being formed. So this diagram is used, and for the sometime you can, if you are plotting your data and it is falling in MVT type, then you have a carbonate hosted Mississippi Valley type of ledging deposit. So you can use it for the exploration, and that is very, very common. So next question is by Saurabh. Is fluid inclusion and mineral zoning be related with each other, and how? Mineral zoning is basically you have the two type of mineral zoning. One is the growth zoning, another is the color zoning. Now, why it is being seen? There are another big lecture on that. Why the color zoning is there? Growth zoning, yes, certainly growth zonings are there, and growth zoning will be there in each mineral, because the crystal grows as per the from a small unit cell, and therefore there will be a growth zone. And in growth zones, you have the entrapment of the fluid inclusions, and those fluid inclusions are the inclusions which got entrapped during the formation of that particular mineral. It means they are the primary in nature. So fluid inclusions in the mineral growth zones are always same, and they are primary in nature, and therefore they are very much related, right? And most of the primary inclusions we study by knowing the growth zone, by using the, because in normal microscope we may not be able to identify the growth zone. So what we do, we use the cathodoluminescence, and we identify the growth zone, and then see the fluid inclusion in that growth zone. So hope it's clear, and if still you have any doubt, you can ask.
Sir, we have taken all the questions from YouTube live chat box.
Okay. So with this, I thank you very much, yes, Ajay and Garima, Saurabh, for giving me some good time on Sunday to interact with the youngsters. I understand that this is a complete subject and requires a lot of time, but in the limited time of 2 hours, I tried to cover all the aspects, and I hope that some of you will have some interest in this particular technique.
Yes, sir,
Thank
we have received a lot of feedback regarding this. All are enjoying your talk, and you have presented your all information and knowledge in very precise form. Thank you, sir,
Thank
for this talk and this your time. And we also thanks to all our participants who are joining with us in today's talk. Now we will meet you on next talk on 22nd July at 4 p.m. On that day, our presenter is Dr. Ajay Kumar Pihani, and the topic is structure and tectonics of Himalaya. So till then, take care and bye bye.
Okay, thank you. Thank you.
Thank you, sir.